So now that we know what equilibrium is about from a chemical perspective, there's this KEQ or KC, there's this equilibrium constant that the system tries to hit. Let's talk more about what K actually means from a physical perspective. Um, it really is a measure of how much a reaction likes to be in either reactant form or product form. Okay? And so we're going to explore this idea again with a potential energy reaction coordinate diagram. Which we should get used to sort of being able to draw and understand in terms of their form. And I know we went over these before, but real quickly, if we kind of have reactants here, and then we have an activation energy, and we have products here, and this is just an example where we have an exothermic reaction. Here's where our reactants are. I'm just going to write them as R, and here's where our products are. We're going to write them as P. We understand that this is a good way of signifying energetically what's going on with a reaction. To go from reactants to products, you have to overcome a certain activation energy. All right. And then so this is our E sub A. And then to go from reactants to products, there's a certain delta H that's given off, or delta H associated with that process. In this case, energy would be given off in the form of enthalpy. Okay. Now, when we talk about equilibrium, right, we not only have to see this as, all right, there's reactants possibly going to products. For equilibrium, there's also products going to reactants. Remember, it's not just one direction anymore. The way we write a reaction is there's a certain defined set of reactants and products, and it looks like the progress is this way, but realize that we can reverse it. We can go in the other way as well. So, oh yeah, and if you look at something like P going to R, right, there's a different activation energy. It looks like the delta H plus the original E sub A going in the forward direction, okay, gives you the new E sub A for the reverse process. So this green line represents E sub A for the reverse process, right? Because the hill is more going in this direction. So what does K physically mean? Kind of think about it as where the reactants and products like to be, right? And if we go back to the functional form of K, remember that K has product information on the top and it has reactant information on the bottom, okay? So we're going to talk about different limits of K and different kinds of Ks that we see. And we can always think about this hill. And it's kind of like if you had a bunch of guys up here, a bunch of balls, and let's just say that they're balls that are going to roll downhill. What K tells us is where these guys would rather be, right? It tells us what proportion of these guys are going to roll down to the product side versus what proportion of these guys are going to roll down to the reactant side. So just a couple little quick examples. What happened if K was really big? Or let's take a simple case. What if K is greater than 1? If you think about K being greater than 1 and you look at this functional form here, K greater than 1, because K is a number. How do I get a greater than 1 number here? Well, then that means the product concentrations are bigger than the reactant concentration at equilibrium. So what this tells us is that more of these guys are going to roll down this way versus rolling down this way, right? K is greater than 1. The numerator must be bigger than the denominator. The numerator contains product information, okay? Let's look at the reverse case, okay? K is going to be a number. Sometimes that number is less than 1. And if K is less than 1, think about what that means. Well, mathematically up here, to get a K that's less than 1, what I have is a situation where, oh, the denominator must be bigger than the numerator, okay? When things have a choice of being on the reactant side or the product side, for a K less than 1, they like to choose the reactant side more. So there will be more of a flow down this way to get to equilibrium than this way, okay, for a K less than 1, right? So K really tells you what side is favored, where things like to be, okay? So if I have just a random situation that I'm trying to analyze, all right, what we have to realize is that K dictates the favored direction. Based off our arguments before, if K is greater than 1, then we know that the products are favored. And whenever you see PROD, I'll try to write it more clearly. Whenever you see PROD, that's going to stand for the product side. Based off our arguments that we just made, when K is less than 1, the reactants are favored. Now, here's the thing that's conceptually important, but also a little bit difficult to grasp right away. This is the favored direction. It's the favored direction at equilibrium. And that's the thing to remember with all this. We're going to start a bunch of reactions away from equilibrium. Now, the reactions always progress to try to hit equilibrium. And then depending on K, we can say once they hit equilibrium, which side is favored. But K tells you the favored position of the reaction, the favored direction of the reaction at equilibrium. Well, what if we're away from equilibrium, which is often the case when we're running a reaction? Reactions don't generally start at equilibrium. When we're away from equilibrium, and it's often the first step of most equilibrium problems that we run into, when we're away from equilibrium, what we do to decide how the reaction progresses is we calculate what's known as a reaction quotient. And this goes back to the idea that K is a target. And if K is a target, then what we do is we define Q as having the same functional form of K. So the way that you calculate a Q is you use your product information on the top, you raise the stoichiometric coefficients as needed, you put your reactant information on the bottom, you raise the stoichiometric coefficients as needed. It's the exact same functional form as K, right? The only difference is that you're using initial information. You're using initial information, you're using setup information, okay? And then K, right, is the target. So if you kind of look at this mathematically, it looks the same as K, but what if this ratio that's established here isn't at K yet? Reactants and products, there will be motion. There'll be an exchange. There'll be, things climbing hills in the potential energy reaction coordinate diagram, exchanging positions. The products and reactants change in a Q until Q equals K. So the reaction quotient, our Q, tells us how a reaction will progress, right? Will more products be made or will more reactants be made, right? So let's take a look at some examples. Quick little example. All right. So let's take a situation where we have a K that's equal to 10. Okay. And we're eventually going to apply numbers to this, but or like actual calculations to get these numbers, but let's just kind of go through this it's kind of simply to start with. And let's say that we have a real simple reaction like R is in equilibrium with P. Okay. Now, let's say that we get some initial information, right, where we have a Q that's equal to 1, right, a Q that's equal to 1. Now, if I look at how I would calculate Q, I would say, oh, well, it's some initial bit of information. It's my product information over my reactant information, okay, and that equals 1. This is my initial information. My K for this scenario, right, my K for this scenario is going to be equal to 10. And it looks like the exact same form. And the only difference is, and I'm going to use the subscript EQ, is that at equilibrium, all right, this ratio is going to equal 10. So here we go. P over R to start with, because remember Q uses initial information. P over R to start with is 1, right? P over R, the goal, the target, what this reaction tells us should happen, P over R should give us 10. So what's going to with my initial information to sort of change to make this occur, right? we have a situation where Q is less than K. So what the reaction is going to do is the reaction is going to take reactant and it's going to convert reactant in the product. Now, how does that make sense? If we have this ratio and we're getting 1, and we need this ratio, dictated by the chemistry, we need this ratio to be 10, then the only way to make that occur is if you make more product. I like to kind of focus in on the product when I do these problems, and I'm going to just kind of explain that one more time. If I look here, here's the product. 10 is my goal, right? And these guys are proportional to each other. So when Q is less than K, I don't have enough product. And if I don't have enough product, what the reaction is going to do is it's going to take reactant and make product until you hit your goal. All right. So my equilibrium P will be more than my initial P because K is the target. Right. Now with the same sort of logic, right, what happens if we have a setup here where we have the same simple reaction that we're analyzing, and Q is equal to 100. Well, wait a second, okay? If Q is equal to 100, this means, product over reactant, same functional form, right? Q is 100, but for this reaction, K is 10. And K is always the target. It's where the reaction is going to go with this information. So wait a second, if I look here, here's the numerator, it's 100. I need to get to 10. I have too much product. So when Q is greater than K, I have too much numerator, right? There's too much product. So what's the reaction going to do to hit this target to get to equilibrium? The reaction is going to put, right, more product into the reactant side, right? The reaction is going to proceed taking product away and making reactant, okay? Now you could have a situation where Q equals 10. Now in this situation, right, what you'll notice is, okay, well, my initial product information, my initial reactant information, oh, wait a second, I'm already at my target. So do these guys want to change at all? Well, no, they already have reached their concentration ratio that are needed, or that is needed for this problem, okay? So if you take a look at this then, right, we have a situation where Q equals K. Will any motion occur here? No. So actually in this situation, these guys, these concentrations, they're already at equilibrium. You're already there, so there's going to be no motion. It's not like the other cases that we discussed, okay? So just a quick little recap that's really important, and then we'll get into one last example, all right? When Q is less than K, all right, what ends up happening is there's not enough products, so the reaction goes to the product side. The reaction moves to make more products. When Q is greater than K, there's too many products. We have too many products to get to our ratio that we need, to get to the K that we need. The reaction is going to make more reactants. Product is going to leave because we have too much of it, and you're going to make more reactants. And when Q is equal to K, then you're at equilibrium and nothing changes. There is no net movement. So K is a target, and Q tells us how far away we are from our target and how the reaction is going to progress to meet that target. Okay? Real important idea, and we use it at the beginning of most problems that we do in equilibrium. All right, so let's take a look at some slides. I'm not going to try to awkwardly hold these up this time. So let's look at the reaction. So you can look at your equilibrium slides if you want to, but I'm going to write a lot of the information down. So another example, let's take a look at this reaction. 2N2, sorry, let me start writing over again. Let's take a look at the reaction. It's actually ammonia formation. So we have 2N2 gas plus 3 H2 gas. We would write this as a single arrow last semester, but now we're going to give it a chance to be a double arrow. All right. So we're going to write this as 2NH3 gas, and I didn't balance it right. I think this is just a single N over here. Okay. So we have N2 gas plus 3H2 gas giving 2NH3 gas. Okay. And what we're going to do is we're going to look at a series of initial concentrations. So if you look at that slideshow and you kind of follow along, all right, what you're given to start with is, let's say that we have an initial N2 that equals 1. Let's say we have initial H2 that equals 1. And let's say we have an initial NH3, right, that equals 0. Now, for our concentrations, we always report with units, and we're going to use molarity until we don't. We're going to use molarity for concentrations, and for pressures, we're going to use atmospheres. And what I mean by until we don't is I'll tell you when we're using different concentrations, but we're pretty much going to stick to molarities for our concentrations. Our K's and our Q's, though, we pretend these M's aren't here. We treat them like unitless quantities, all right? But now, so what I want to do is I want to be able to predict now, based off a K and a Q, what's going to happen as this reaction progresses. So if I set this up in a reaction flask, all right, do I expect there to be more N2 after some time, more H2 or less H2? What's going to happen with NH3? We know how to answer that question now. We don't even need to know what K is in this instance, and you'll kind of see why in a second. If I want to decide what's going to happen with this reaction, I calculate a Q. Remember, Q is like our GPS. It tells us where we're going to go. K is the target, Q is like the GPS, all right? So what I'm going to do, if I think about what Q's functional form is I have to take my initial NH3 information, and I'm going to square it. And I'm going to divide that by my initial N2 information, raise it to the first power, and then my initial H2 information, and raise it to the third power, all right? That's my Q. Well, if I plug these numbers in here, what I'm going to get is, it doesn't really matter what happens in the denominator. Q is equal to 0. Now, I don't even need to know what K is, because if Q is equal to 0, that's the lowest value you could get for Q. You can't have negative Q's. They can only be positive. Same thing with K. You're only going to have positive K's, all right? So Q is the lowest value, so for sure, Q is less than K. So in this instance, Q is less than K. So what's going to happen is the reaction is going to progress to this side. And when we get to equilibrium, what we'll end up with is a situation where we have more ammonia and less of the reactants. And if you look at your slideshow that I gave you, but again, I'm just going to write the numbers down here. When we look at our equilibrium information for that setup, right? We see that our prediction with Q being less than K manifests as the equilibrium concentration goes to 0.921 molar for N2. The equilibrium concentration of H2 is 0.763 molar, and the equilibrium information for NH3 is 0.175 molar. 0.157 molar, sorry. So what happened? Relative to the initial information, the reactant concentration went down, right? And relative to that initial information, the product concentration went up, just like we predicted with our Q. Now we do have equilibrium information, and now we can actually calculate a K with this. And so we can take this, and remember, initial information is given to our Q, but equilibrium information is given to our K. So if I take this and I put 0.157 into it, squared, all right, take my N2, 0.921. Notice I'm not using units here. We get to pretend these guys are unitless. Oh, my 0.921 is going to be raised to the first power, right? Take my H2 information, add equilibrium. That's why I'm allowed to calculate a K. I'm using equilibrium values, 0.763. And cube it. What you get out for K is you get a number, and this number is 0.0602. All right, so the correct number of significant figures. Now this tells us that at equilibrium, because now we're at equilibrium, right? At equilibrium, K is less than 1. So what that tells us is at equilibrium, you expect to see more reactants than products. Okay? So we were away from equilibrium with Q, we got to equilibrium, and now we get to analyze K. And K is less than 1. Okay, we'll take a look at this. Here's my reactant information, and here is my product information. Which one of these sets of numbers is bigger? Oh, my reactants are bigger than my products in terms of concentrations. It makes sense that my K is less than 1. There are 2 other examples in the slideshow. I'm just going to do them real quickly now for the same reaction, just to stress this idea and emphasize it again. And remember to take some breaks, make sure you kind of digest, rewind as you need to, take notes, come up with questions that you're going to ask me, all right? Let's look at another set of initial information. Again, we'll do this quickly, all right? In that slideshow, what you'll see is then there's another set of initial information. So what if we set this up differently, where this is 0, and this is 0, and this is 1, all right? Pretty simple situation. We know what K is now. K is set for this reaction. We can even write down at the top now. We're able to use the information from the previous slide to know that this is 0.0602. All right, that's what K is. If I take a look at this, now what's going to happen with this initial setup? Well, with this initial setup, when I go to calculate my Q, because remember, that's going to tell us what's going to happen with the reaction. Q is the GPS, K is the target, okay? Well, I'm going to put 1.000 here, and I'm going to square it. And then denominator only have zeros. Okay. Well, anything divided by 0 is really, really big. So this semester, to kind of simplify the thought process, anything divided by 0 is infinity. Okay? So now if I look at infinity versus K, oh, in this situation, Q is greater than K. And in this situation, I have too many products. So what happens is the reaction is going to progress now to the reactant side. We expect this to go down, and we expect these 2 to go up. If you flip your slideshow, what you'll see is that's what happens when we look at the same information now. All right? Because we got a Q that was so big we called it infinity. We had way too many products. So we're going to get shifting to the reactant side to get to equilibrium. All right. What we end up with is a situation where at equilibrium, this is 0.399 molar. This is 1.197 molar. And this is 0.203 molar. And again, the numbers aren't surprising. We have more concentration of reactants than products at equilibrium because our K is set and our K is still less than 1. But look at how those numbers changed. This went down from 1. These came up to 0 because our Q was greater than K. All right, our Q was greater than K. All right. The last example from the slideshow. All right, I want you to try to do on your own. Maybe pause this. Remember that we know what K is. If I give you another set of information, all right, if I give you 2.00 here, and this is initial information now, I give you 1.00 molar for initial information. Initial. And I give you 3.00 molar for initial information for your product. Can you calculate what Q is, and can you decide what's going to happen? So you should be able to calculate Q. You figure out what this number is, right? What you should be able to show in this situation when you plug all this in is that Q is greater than K, all right? So it's another situation where we expect, and you do this math right here, okay? So it's another situation where we expect, all right, when you go to the equilibrium, all right, when things work towards that equilibrium sort of target, we're going to again get a shift where these go up and this goes down. And I'm just going to write them right here. Here's what happens at equilibrium. This turns out to be the case. This turns into 2.59. This turns into 2.77. And this turns into 1.82. Right? So this went down and these went up. Okay? So a lot of critically important things here. Q versus K checks. Q versus K. How Q compares to K is something that we do at the beginning of every problem. It tells us which way the reaction is going to go. See K as a target. See it as a way that decides how much reactants and products you have at equilibrium. Okay? But it's a target. So if I set up a reaction at any sort of set of initial information, I'll be able to do a Q versus K check and be able to direct which way the reaction is going to progress. Okay, a lot to digest, all right, but that's it for this video. Please make sure that you take down any notes or questions that you have for me and communicate them as soon as possible.